Okay, welcome back everyone. This is lecture 2 in our biomechanics, virtual biomechanics course. If you remember back from the first lecture, we talked about kinematics, which we had kinematics and kinetics. Kinematics were the descriptors of motion. They can be quantitative and they might include things like joint angle, speed, describing where a body is in space. Most of what I'm going to do the rest of the lectures will be more kinematic based. But this second lecture will look at kinetics, which remember is the force side of biomechanics. And this, for a person who is less of a clinician like me and more a true biomechanist, there's a lot of focus in kinetics and force. And in a typical college course, we would do a little more of this because I would assign math equations. Don't worry, I won't give you any math homework after this lecture, but we're just going to introduce some concepts. It helps in terms of understanding forces on the human body and how our tissues respond to different types of forces, and then thinking about certain types of injuries, compression injuries, injuries where there's bending forces on our body, or tensile, tension type forces on the body. So this lecture has some concepts that are important as we start getting into specific regions of the spine, or of the body. We might be in the spine and looking at compression fractures in the vertebrae. So we'll want to understand how forces can affect human tissue. So let's jump into it. Just ahead of time that this has a little bit more kind of math type stuff in it and equations and things, so just tough your way through it and we'll get to the joints soon. So when we look at kinetics, first we want to talk about mass. We probably all remember learning about mass. Maybe you've had it in college in physics, or maybe back in high school, something like that. But the definition of mass is the quantity of matter composing a body. It's represented by the symbol, the lowercase m, and the units are kilograms, right? So mass is going to be is one of the most important things, especially when we're talking about force, because we're going to see force equals mass times acceleration. And remember, in dynamics, in biomechanics, that sub-branch dynamics, we're looking at acceleration when there's some acceleration in the system. So then we can start looking at calculating force. We'll have a mass of an object, and I'll show some sort of real life examples here where maybe you're thinking about a person's mass and their acceleration. Maybe they're landing on a force plate, and we can take the force plate is going to take all that information, the mass and acceleration, and calculate force in newtons. So mass is really important. And then when we think about just a basic definition of a force, it could be a push or a pull. It has magnitude and direction and a point of application. And again, that formula, force equals mass times acceleration, and the units are newtons with an uppercase N. So when we think about characterized by magnitude, direction, right, this will be, if you remember, if you ever had physics, maybe you did a free body diagram, and in those diagrams, when something's hit, maybe an object is hit, there's an arrow, a vector that comes off of that, and that represents the force. And that arrow will have a certain direction, so to show the direction the force is contacting the object, and then the length of the arrow represents the magnitude of the force. So a shorter arrow will be smaller force, a longer arrow. And so we do these free body diagram questions where you look at all of the forces acting on something. So maybe you've got a tennis player hitting a tennis ball, and so you look at that ball, that tennis ball, you have the force of the racket on the ball sending it one direction, right? That's one force. And then coming back on the ball, you've got air resistance. So the air resistance is creating an opposite force. So those two forces are going in opposite directions, so there's going to be some sort of canceling out of force to get the net force. And then you've also got gravity acting on the ball. So gravity is a force and is going to have a downward pull, which is, obviously that ball falls over time if it's not hit again. So you've got all these forces acting on various objects, and you can work through in those free body diagrams and figure out what's the resultant net force that's left over, and that's what happens to the object. So again, just important to remember, simple definition of force, and that this equation, force equals mass times acceleration. Here's a video. So this is from a lab that I used to own, and this is a force plate you can see there in the ground, and this individual was a high-level volleyball player, and when she's landing on the force plate, it's showing the ground reaction force vector. So if you look at that vector, it is equal and opposite to the force she's putting into the ground. And as she lands, that vector has direction and magnitude. So you can see it points, and you can see the length of the green line changes over time based on how much force she's putting into the plate. So I like this one because it's a type of force, it's ground reaction force, and it shows some of those things we just talked about, magnitude and direction of the force if you look at that green line. So anyway, just kind of a real life example, again, just to see a force plate in action. So here's that free body diagram. I mentioned the tennis ball before, so this is basically showing that thing I just explained. So the tennis ball is being hit by the racket on one side, and that vector is longer because it has the force from the racket, and then opposite force is the air resistance, which has a little shorter vector, so smaller magnitude force, and then the weight of the ball is going to be working with the acceleration due to gravity and creating this downward pull from gravity. So it's going to pull. So you have all of these forces acting on the ball, and then through vector addition and subtraction, you can put them all together. And as you might imagine, the ball is going to want to keep moving the direction the racket hits it, but also go down a bit. So you can take those three vectors and add them together and find the resultant, the net force on the object. So here, just speaking of net force, so net force, the definition here is the single resultant force derived from vector. So vector composition is basically adding and subtracting forces and getting the one vector that's left over, so your net force. Or you can think of it as the force that determines the net effect of all acting forces on a body. So it basically is the leftover force. When you put all the forces together and some cancel out, some might stack on top of each other, it gives you the total sort of net force left over in the system and tells you what direction the object's going to move and what sort of magnitude force is on it. So that's basically the idea. Torque. So torque we'll talk about a lot, because especially in the muscle, when we're thinking about muscles, because muscles basically torque is a rotary type force. So it's force that's creating rotation. And if you think about our joints, when our elbow flexors, for example, pull on the radius and on the radius, they are creating a rotational force. So that's creating torque. So really, torque is a really applied. We think about this all the time in the body. So, or you can think of it as the angular equivalent of force. And when we calculate torque, we're going to look at the force that's being applied to the system and the distance perpendicular. So that symbol there, the lowercase d, with this sort of 90-degree, almost upside-down T-looking symbol there is the distance perpendicular. So it's showing that right angle. So you're basically torque equals force times the distance perpendicular, and that will give you, so you can almost think of this as like that's going to give you the torque, but you can almost think of these sort of drawings as like a seesaw or a teeter-totter, whichever term you're familiar with. But if you've got an axis in the center of a seesaw or a teeter-totter, imagine that's like the joint axis, and then you've got two kids on either side. They are each creating torque, and maybe one kid weighs more than the other, or maybe one kid is sitting closer to the axis, one's farther away. That's going to change the torque on each side, and it's going to determine which way the teeter-totter tips. So, if you look at this situation here, we had a force of 10 newtons, and the distance perpendicular is 2 meters. So we're going to take 10 newtons times 2 meters, and we get 20 newton meters. So torque will be represented in newton meters. And again, this is how we would calculate the torque created by our muscles. That muscle is pulling on the tendon, that pulls on the bone and creates a rotational force. And we could, we can explain that in terms of torque. So a bit there. And then this is how we measure torque in an objective way. This is a dynamometer, and this is a baseball player that I had on this, and we were looking at his quadricep and hamstring torque. So it's a really objective way to measure strength. So that machine, he has to push and pull against it each direction, and it will tell us the amount of torque that his quads and his hamstrings can generate. In this machine actually outputs it in I can't remember the actual force, but it doesn't display it in newton meters, but that's what it measures. So you can see machines like this one's called a Biodex. It's a common dynamometer for measuring torque. You can move it around and change the position so you can measure, you could measure the rotator cuff on this, you can measure the glutes, you can measure lots of different muscles. So just a real life example of how you might measure torque in an applied setting. Okay, and then center of gravity is the point around which a body's weight is equally balanced. It also it serves as our index of total body motion. It's where the weight vector acts on people. So, if you were just standing still on a force plate and you could see the ground reaction force vector, it would basically point right up to your center of gravity, which a lot of times they talk about this for guys and girls being kind of around the belly button, sort of in that region. So that's where we think of the center of gravity. It's also referred to as the center of mass. So you'll hear both things, but it's basically where gravity is going to act on an individual. And again, you can really see it when they're standing still. So, and then if you have, when you think about thinking about torque, just the concept here that, again, back to kind of that teeter-totter or seesaw example, we've got two different forces on either side of the axis here, the center of gravity. So you've got the center of gravity, which we just talked about here in the middle, center of gravity, and then we've got forces on either side and right. These are different forces, but because they're at different perpendicular distances from the axis, they end up balancing each other, right? So on this side we've got 10 newtons over 2 meters, so we've got 20 Newton meters, and over here we've got 20 newtons at a meter away from the center of gravity, so we still, again, get 20 Newton meters. So, you kind of you can think of this in your body. You would think about agonist and antagonistic muscle groups. So if you've got your elbow joint and you've got the elbow flexors on one side of the joint and they're attaching a certain perpendicular distance from the joint axis and pulling with a certain force, and then you have your triceps, your elbow extensors on the other side, those agonist and antagonistic muscles are exactly like this teeter-totter or seesaw. They are working against each other to keep the joint balanced. Or you might think about another example would be, imagine if you're in a push-up and you go down and you hold your push-up right in the middle point, say. In that example, your triceps have to contract isometrically to balance out. So they're creating torque, your elbow extensors are creating torque, and they have to create enough torque to match that torque that's created by gravity trying to pull your body to the ground. So again, you have this balanced situation where you've got opposing forces acting on the joint, and your triceps are exerting enough force to balance out gravity's effect, and that creates that isometric contraction. That's basically what we see in most isometric contractions where body weight is the load on the system. So just some examples that might help make that clear. Weight is the attractive force that the Earth exerts on a body. So weight, this formula, if you notice here, weight equals mass times acceleration due to gravity. This is the exact same formula. The other one, remember, was force equals mass times acceleration. Weight is a force. So we use the term weight in normal life a little differently. We often use it a little more like mass, I think, where so people will sometimes confuse these things. But weight, from a physics standpoint, is a force. So it's just that the acceleration portion of it, you would have, if you were calculating your own weight force, you would take your mass in kilograms and you would multiply it by the acceleration due to gravity, which gravity is this constant acceleration pulling you towards the Earth at 9.81 meters per second squared. So that would give you your weight force. If we look at the definition of weight, it is the point of application of the weight force on the body's center of gravity. So the weight force is the point of application of the weight force on the body's center of gravity. And again, because it's a force, weight is going to be labeled in newtons. Pressure, so we look at this one, pressure we talk a lot about. If you think about things like how your foot is contacting the ground or where you're putting force sort of in your shoe or something like that, we think about those type. This is an area where pressure comes up quite a bit, and it's the force per unit area. Or maybe think about blood pressure. That's another one where this where we would measure where this would come up. So force per unit area over which a force acts. We see this with fluids, like I said, blood pressure, water pressure. And because it's force per unit area, it's going to be newtons divided by meters squared. The other thing that is calculated the exact same way as pressure that I probably end up talking more about in terms of rehab and exercise is stress. And it's calculated the exact same way, so it's force per unit area. And this is usually reserved more for solids, so it's used more commonly with the human body. So again, newtons per meter squared, force divided by area squared. But you might think about stress in joints, so this comes up with osteoarthritis. So if we're thinking about somebody who has arthritis of the knee, we would be concerned with how much force and over what area is that being spread in their knee joint, and how is that affecting the progression of arthritis in their knee. So that's one example where, the one that comes up quite a bit in my mind is thinking about osteoarthritis and stress on the joint. But it's one that comes up a lot because it has to do with solids. We use this quite a bit in the human body. So, this diagram can be useful for looking at, thinking about stress. So if you've got force acting on so imagine maybe this is the proximal surface of the tibia. So you're thinking about the knee joint, and the femur is pushing down on the tibia, and you've got this larger surface area with these forces coming down. Maybe this is the meniscus. Right? So maybe this is a person with a healthy meniscus, and they're spreading this force out over a greater area, so the stress on the system is lower. And then maybe over here we've got all these forces, these are longer vectors, so we've got greater force, and you've got the smaller area. So maybe this is a person who had their meniscus debrided and they're missing part of it, or they have a tear in their meniscus, so we've got this extra force coming down over this smaller area. So the stress on that system is going to be quite a bit higher. So it can be a good visual for just thinking about force, the magnitude and direction of the force, and then the area over which it is being applied, and how that creates stress on a system. Volume, this one, we're not going to talk about a whole lot, but it's basically the space occupied by a body. It has, unlike area, it also has depth, so you've got width, height, and depth, so you'll see meters cubed or centimeters cubed. We're not going to use it a whole lot, but if you remember back, we talked about anthropometrics, so if you were looking at the size and shape of body segments and calculating their size, then volume would be important. I'm not going to talk about it a whole lot. Density, the mass per unit of volume. So this, I just said I wasn't going to talk about volume, but this is one area where volume comes up, especially in bones. I'm sure all of you are familiar with thinking about osteoporosis and osteopenia, but these conditions of decreased bone density, an area, one pathology, and we'll do a lecture later specific to bone tissue, but bone density issues are, a huge one that if you're in the rehab or training community, as people get older, we're really trying to help boost their bone density so that they don't suffer fractures and disability in life. So one area where density really applies in the human body. Okay, so we want to start talking about some of these forces, which I mentioned at the beginning of the lecture. So one here is compression force is one type, and you can imagine this is a pressing or a squeezing force. In these images, I think this makes me think of the spine. So maybe you've got one vertebrae, and maybe the black area is the intervertebral disc. So maybe this is L4, and this is the disc, and then we have the L5 vertebrae. And as you're standing or sitting, you're putting compressive force through the spine onto the vertebrae and the discs. So that might be one example, or maybe we could go back and think about the meniscus I was talking about before. So maybe this is the two bones coming together. Maybe you've got the femur and the tibia, and this is the meniscus. And when you're standing, you're putting compressive force. So one type of force in the body that we encounter all the time throughout the day, compressive force. And then we can have compression injuries. Here's a compression fracture where the vertebral body has experienced a compression fracture, where basically that compressive force can break the bone. And this, I actually, yeah, my dad had one of these, slipped. It was kind of funny. Slipped in. We had a puppy, and he slipped on puppy pee that he didn't see and fell and landed on his tailbone, and ended up fracturing, I want to say, his L4 vertebral body. So impact fractures like that. It's winter right now in a lot of places, so people slip on ice and land on their butt, and compression fractures like this can happen. Sometimes it happens without a real trauma, and older individuals who are very osteoporotic, they might get these just with, something very minor, bending over or sneezing or something, where if their bone density is very compromised, it could injure the bone. So just an example of a compression injury. And then we have tension. So basically, kind of think of the opposite. You're pulling two things apart. It's a pulling or a stretching force. This is happening all the time when we contract our muscles and the tendon pulls on the bone. So this makes me think of injuries in that the muscle tendon structure, where maybe somebody's contracting really hard and they tear the tendon off the bone. They have an avulsion type of injury. They pop their Achilles tendon, right? It pops off the bone. Those are usually tension type injuries. So you see that a lot in tendon injuries, and I think I have a video here. Yeah, so if you watch this guy, maybe you've seen this before, watch his left arm, the arm that's supinated. As he pulls, his bicep is going to avulse. Pop, you see it right there, it pops off. You see his bicep pop off. I'll rewind it here so you guys can see it, but watch as he pulls with that supinated arm, this bicep pops out, there it goes. So did you see that? One more time here. Watch that bicep right there, boom, pops off. So this, these bicep avulsions, pretty common muscle group, and he doesn't even know what's happening. And then he freaks out when he sees it, which brings in a lot of pain neuroscience stuff, which is always interesting. But, so he pops that off, and, again, this is a common one in the biceps, and a lot of people don't have it repaired unless they're an athlete and they really need it, because you've got other elbow flexors, brachialis and brachioradialis. But that's a great tension injury, so it's the force on the system was too high, and we'll talk about when you reach this yield point, you hit the yield point, and the tissue changes shape and tears, and it can't return back to its normal shape. I mean, it's fully popped off the bone there. So anyway, a good tension injury. And then we've got shear forces, which are basically two surfaces sliding parallel to each other. Maybe you think about this with if somebody's tore their ACL. If someone tears their ACL and their tibia and femur are sliding more than they should against each other, there's this sort of extra shear type of movement that that makes the joint unstable. I mean, this is what people will experience with ACL tears. Some people will experience, that's one of the questions we ask them is, do you feel unstable? Does your knee feel unstable? And that's what we're trying to get at, is are the bones kind of moving on each other? And because they'd be moving parallel like that to each other, it would be more of a shear force. Or maybe you think about this in the spine. If somebody had a fracture or some instability, maybe you could have two vertebrae kind of moving on each other a little more than they should. So ACL is probably a better example. But these are forces directed parallel to a surface. So we've got that one. And then the last one here is bending. Bending forces have both compression and tension. So you imagine taking like a stick off a tree and snapping it, right? As you put that bending force on it, on one side it's being compressed, on the other side it has tension, and at some point it will, probably the structure will fail. And so bending forces, I think of these with certain types of fractures. Some people, especially in kids, kids can have these green stick fractures where it's sort of a bending fracture and it only breaks one side of the bone because kids have more flexible bones, so it doesn't snap all the way through like it would in an adult bone. So that's one I think about. But so you've got the bending forces. Oh, here's that green stick fracture. So you imagine as the forearm is bent here, the bone, you can see there would have been bending forces over here and compression forces. So the bone's being bent. So you have compression on this side of the bones, tension on this side. It looks like the bone snapped on the side that was undergoing tension. And again, these green stick fractures you see more often in pediatric cases because again their bones are just more flexible than adult bones. The adult would probably just snap all the way through. Okay, so a good example of bending forces. Oh, and then torsion. Yeah, so torsion is sort of a twisting type of force. around that longitudinal axis. We talked about the longitudinal axis, like if you're imagining pronation and supination in your forearm, that longitudinal axis is going through the segment longitudinally. So that's sort of the same type of thing. Maybe this would be something like if you've ever heard of a spiral fracture. There's a twisting in the bone. A guy in my physical therapy class, actually, two guys were arm wrestling, and this happens. I think this injury, it's uncommon but not unheard of in arm wrestling, but yeah, one of the guys ended up getting a spiral fracture through his humerus as they were arm wrestling, and basically almost like a torsion kind of spiraling fracture through his humerus, and associated with a strong, in arm wrestling, you're trying to rotate your shoulder to beat someone. And so there's putting this huge rotational force through that longitudinal axis on the humerus bone, and in his case, it just snapped it. So maybe that's an example to help you think of this. Okay, this is a really important concept. This is the load deformation curve. It's huge. It's going to come up from time to time. We'll talk about it with different tissues in the human body. You can apply it to non-biological things like metal and glass, and basically you're taking a tissue and you've got these you're taking some structure and you're applying a force to it, and you're looking at deformation is a change in shape. So you're kind of looking at how much can this in the body, how much can this tissue change shape, and what happens to that tissue. So basically, if you take a bone, if we took one of your forearm bones and we put it and bent it, right? It would be able to change shape up to a certain point. So that's this elastic region. It's a point where you could change its shape, but then if you let go, it would go back to normal. So the elastic region means it will return back to its normal shape. But then eventually, we all know, you take bone to a certain point, it will start to yield and snap. And so the yield point is where you're changing shape and you're starting to go into this plastic region where if you take the force off, it's not going to go back to its normal shape. It's going to stay permanently deformed. And then if you keep going too far, you hit the ultimate failure point and the whole structure just fails, and maybe you get in the bone you have a full fracture, something like that. So this will happen in all our different tissues. We can think about it with muscle, right? Muscles and tendons have a much greater elastic region than bone. But eventually you hit a yield point where they start to maybe experience a strain and tearing, and maybe, and then you're in a point where it can't fully recover, and then you hit all the way to this point, maybe like a tendon avulsion like we just saw, where you go so far and deform it so much that the thing just fully tears and it's just done. It's not going to recover. It's ultimate failure. So this can be helpful to think about, and it's something we'll talk about from time to time throughout the rest of the lectures. Repetitive and acute loading, I like to talk about these here because we're talking about forces on the system, different categories of forces, and these can be useful when you're thinking about injuries too. With repetitive loading, we all talk about repetitive overuse injuries, so this is kind of that thing. It's repeated application of subacute loads, so they're smaller loads. You might think about this with like a stress fracture. So maybe you're putting a smaller load, it's a runner, it's not a big enough stress to just break their leg in one, or tear their ACL or something. It's a smaller force done many times, and the bone eventually, in the right situation, the bone can start to fail. So a stress fracture would fit more into this kind of repetitive subacute loading. A lot of tendinopathies are like this. If you have an Achilles tendinopathy, maybe you're a runner, and you decide to pick up your running mileage, and maybe you run a little more and you're not fully conditioned, you don't have that capacity yet, and you get a tendinopathy in your Achilles tendon, and that would fit more into this repetitive type of category of force. And then we have more acute forces. So this is one big single force. It's of sufficient magnitude to cause an injury. So that deadlift video was an example just now. It was one big, he had enough load on that barbell. It was of sufficient magnitude to tear the tendon. This could happen in someone who tears their ACL, a soccer player who's running and changes direction. They cut on the field and their ACL tears in one moment. So those are acute type forces where it's large enough magnitude to injure the tissue. So I think most of us are pretty familiar with these. It's almost like repetitive overuse injuries, and then you've got acute traumatic type injuries. Those two categories. And our last slide here, just to put that in a graph, if you're thinking about the likelihood of injury, your likelihood of injury is likely to go up if the load magnitude goes up. So this would be more like that acute loading where you've got a higher magnitude force on the system. So maybe somebody lands awkwardly and tears their Achilles tendon, right? So that's a high magnitude acute loading. The frequency is very low. So maybe it's just one event. So one event of high magnitude. And then on the flip side, we've got things like stress fractures and tendinopathies where the frequency of loading is very high. So maybe it's a runner who's putting in lots of mileage, but the load on the system is pretty low. So the load is low, but the frequency, the volume of loading is really high. And again, the likelihood of injury goes up. So in both of these cases, the likelihood of injury is higher. You're just kind of flipping the variables. So I like this. A graph like this could be useful to you even in your setting working with patients and clients. Maybe a visual like that helps them understand these two ends of the spectrum and how they can contribute to injury. Okay, well, that's the end of the kinetics lecture. So again, I know maybe a little boring. It always is at the beginning of the semester getting into the new stuff. But these things, these concepts will apply as we get into different tissues of the body. We'll look at skeletal muscle, bone, and then we'll start, we'll go through all the joints. So when we're looking at the spine, when we're looking at the ankle joint, these types of factors are going to come up as we think about injury biomechanics. So, all right, until next time, I will see you later. Bye.